Hello, good morning.
Hello, good morning.
Okay, so did you have a look at the topics for presentation? Could you zero in on something?
So we have decided that groups, but have only a tentative topic. We have not like fixed the topic yet. But so Srisha, Ashwant, and I are going to probably present this factorization forest theorem.
All right. Okay. Okay. So you guys decide and let me know. Okay, by this Sunday or something,
Okay.
or by next class, by Friday. That will be easier. Let me know by Friday. Okay. So let me come to today's topic, which is R trivial and L trivial classes. So we already saw that Schulzenberger's theorem gives a characterization of H trivial semigroups. Yeah. languages recognized by H-trivial semigroups. Now let's look at what is R-trivial and what is L-trivial. I mean, these R-trivial and L-trivial classes are not very important because they don't have. I mean, it's not like it's not a theorem uh, because their characterization is easy. But you will see some ideas which are very often used in this in semigroup theory, especially formal language theory. Okay, so first of all, let's talk about R trivial, because when we talk about R trivial, if I want to characterize cell trivial, it will be dual. Yeah, because R trivial is a dual. Everything is symmetric, so we can focus on R trivial. So first of all, if I draw, if I have an S semigroup S, which is R trivial, how will its egg box diagram look like? How will it look like?
Each J class would be like just a column.
Each J class will be like a column. So for instance, I will have, this will be a J class, then there will be this, then there will be this, and then, yeah, so it will be like this. And let's imagine one is that we are talking about monoid, and they okay, so one will be an H class because of the reasons I have told before. And what does R trivial really mean? R trivial mean that if A or B, that implies A equal to B. That's what it means. So can an H class contain, so each of these box cells can contain how many elements?
One.
Yeah. Each cell contains one element. So in particular, the semigroup is aperiodic. Is H trivial bracket aperiodic. Okay. So we know that R trivial monoids recognize. So therefore, R trivial semigroups are a subset of um, aperiodic languages. Yeah. So every artificial language, every language recognized by an artificial semigroup will be uh, star free, can be expressed using a star free regular expression and definable in F1 and so on. Okay, that much we understand. So first, I want to write an equation. So for instance, we wrote for a periodic, we wrote an equation. A power omega, omega plus 1 equal to A power omega, A power omega. Yeah. This was an equation for a periodic. Yeah. How can I write an equation for R trivial language? Sorry, an equation for R trivial semigroup. So I want to write an identity. Yeah, for R trivial. All right. So let's do. So imagine I have two elements A and B. Imagine. Imagine A or B. That means that A is equal to B is equal to AP and A is equal to BQ for some P comma Q. So therefore, I will get that A is equal to APQ. which is equal to A times PQ power omega. Yeah. So far, all right. Now let's look at this. And you will get B is equal to let's just write that one. Okay, so far clear. A is equal to PQ power omega. What about these two elements, PQ power omega and PQ power omega times P? Can you say something about them?
So the left one is r less than equal to the right one.
Okay, and also
Actually, they both
They're
are
equivalent
they are equivalent. Why they are equivalent?
because R trivial implies that it's aperiodic. So
So R
So more
trivial,
like
yeah.
pq the whole to the omega times pq is again pq the whole to the omega. So
Now, if I just multiply by Q on the right hand side, if I multiply this by Q on the right hand side, then I will get PQ power omega plus 1. But we already observed that R trivial monoids are aperiodic. So therefore, PQ power omega plus 1 is same as PQ power omega. PQ power omega times P times Q is equal to PQ power omega plus 1, which is equal to PQ power omega if the semigroup is aperiodic. Semigroup is R trivial. Yeah, because if it is R trivial, then it is aperiodic, as we have seen. So PQ power omega is R equivalent to PQ power omega times P. So therefore, PQ power omega plus 1, no, sorry, PQ power omega P is equal to PQ power omega is satisfied by R trivial monoids, R trivial semigroups. Is that okay? Whatever I just did.
yeah.
So if um, so why did I talk about A and B? PQ power omega times P is equal to P. Um, Maybe I confused you a little bit. Let me state the state it as a proposition. The following are equivalent. One, for racemi group S. S is R trivial. Every regular D class is R trivial. Third one is S satisfies the identity PQ power omega P is equal to PQ power omega. So what do you mean by identity? You take any semi-group. What do I mean by satisfying an identity? I have an equation like this: PQ power omega equal to PQ power omega times P is equal to PQ power omega. What I do is that I take a semi-group S, and P and Q can be assigned any element of the semi-group, and omega power omega is, you look at the unique idempotent power of that element, and then for any assignment, the left hand side should be equal to right hand side. Okay, so what is this proof? So if S is R trivial, then so let's 1 to 2 is obvious, because if S is R trivial, then every regular D class. What is regular D class? A D class which contains an idempotent. Hello?
Yes,
Yeah,
sir.
yeah, we can hear you.
Yeah. So if S is R trivial, then every D class of S is R trivial. And in particular, every regular D class is R trivial. So 1 to 2 is obvious. 2 to 3 is,
Sir, just one question.
yeah.
So since we're using the idempotent power here, the semigroup S is, I mean, we're working with finite semigroups, right?
Yeah,
Or-
finite semi. Yeah. Sorry. Finite semi. Okay. I don't know if it will hold for infinite semigroup, because probably it won't hold for infinite.
Why did you say it should be finite?
1 to 2.
Why did you say that it should be finite?
In the
Because
third property, we will
otherwise,
see.
I don't think this one will hold, because we are writing it in terms of an idempotent power. Yeah.
Okay.
Because in this proof, I am actually raising it to some idempotent power. That won't be possible if the monoid is infinite.
Yeah. Okay.
Okay. So what is 2 to 3? Every regular D class is R trivial. That satisfies the identity. Because if I have PQ power omega times P as well as PQ power omega are equivalent. That we have already seen. And they belong to a regular D class. Yeah, because PQ power omega is an idempotent. So therefore, when I say that if I have two elements, PQ power omega times P and PQ power omega, they belong to a regular D class, and they are R equivalent. And since regular D class is R trivial, I'll get 3. Is that okay?
Yeah.
Okay. And from 3 to 1, three to
This is the
1,
part that you showed about.
yeah, this is a fact we showed. If A or B, then A is equal to BQ and B is equal to AP, and the A is equal to A times PQ power omega is equal to A times PQ power omega times P is equal to B. Since PQ power omega P is equal to PQ power omega. Okay. And so therefore, that we have the theorem which says that trivial monoids are characterized by this identity. And more importantly, if I want to know the property of a monoid, I just need to look at the regular D class. This holds not just for R trivial, it holds for J trivial, it holds for L trivial, and it holds for H trivial. exercise. So the similar proposition for J. Yeah. So actually, if I want to check a monoid is J trivial, I don't need to know all the D classes. I just need to know the regular D classes. Okay. All right. So now we know how to write an identity for R trivial semigroups. And can you guess what will be the identity for L trivial semigroups?
Q on the left hand side.
You can take Q times QP power omega is equal to QP power omega, something like that. Okay. All right. So that is the identity for R trivial semigroups. Now let's come to our important fact is our important job is to find characterizing languages recognized by R trivial semigroups. Okay. So how will they look like? So let me go back to the egg box. So I have one here, and then some D class is there, some other D class, some other D class, some D class, and so on. So initially, I will imagine I have a word W. Imagine I have the alphabet A. Okay. And initially, I'm starting with the empty word 1. So I start here. And then some word is coming, A1, A2, A3, A4, etc. Yes, up A till A. Some word is coming. Okay. So I'm starting at 1. And can you tell me if I have a D class like this, what about this R class and this R class? Are they comparable? Are they comparable? Like, is one greater than the other, or less than the other, or equal to the other? What do you think? Two R class and a D class. What do you think?
They are not, right?
They are not comparable. Why?
So it's two R class and a D class, right?
Yeah, it's two different R classes in a D class. My question is, are they comparable?
So they are L equivalent.
They are L equivalent, but I'm asking about what is the R ordering between them? Is it like
So
We have
since
already
this is a
yeah,
F1,
yes. China?
yeah, we already proved something like if two elements S and T are J equivalent and they are R comparable, like S less than or equal to T, then it should be in the same R class.
Yeah, exactly. So if they are in the same D class, same J class, if the monoid is finite and if something is in the same J class and one is R less than the other, then they are actually R equivalent. It's sometimes it is called the prefix lemma, but it is a fact about finite semigroups. Yeah. So anyway, the gist of what I'm asking was that the reason why I asked is because, so let's look at the journey of this word A1 to AN. So I start in the first R class, first D class, or I start in 1, and then A1 comes. So if A1 maps to 1, I'll remain the same. I'll remain here. And now if any number of A1 comes, I'll still remain here. And now imagine some A2 comes and then I fall below 1. So I fall somewhere here. Now what I can do is that, so first I am in some R class, and then at some point I fall below that R class. And then I continue like that for some time, and then I fall again. And then I continue like that, I fall again. And I can continue like this. Yeah. So how many times I can fall? I can fall as many times as there are D classes. I mean, it so happens that I can fall as many times as there. I mean, the height of the D chain or the J chain. That's what the common word we use. How many times you can fall? You look at the height of the largest J chain. Chain is, if you have a partial order, a chain is a set of elements which can be linearly ordered. That's what a chain is. For instance, here, this is a chain like this. So yeah, so this is how your word will look like.
Also, like within a J class or a D class, we can't switch between R classes, right?
Yeah, within a D class, you cannot switch between R classes. That's what my first
Right,
question was. So I'm not, I'm staying in the same D class for some time, and then I fall. And if I fall, I'm not coming back.
No, so I'm saying like even if you stay in the same D class, more
Yeah.
specifically, you stay within one H class. Right?
Yeah, one H class. Yeah, exactly.
Okay.
Okay. So imagine I have so imagine, so, um, the idea is clear that I can fall some. So imagine I have a word A, B.
It's 11 o'clock.
A. Okay. And I am in an R class. Another, imagine I was in an R class. I read A, B, and I am in an R class. Another A comes. I still remain in the same R class. Now, can another A come and can I fall below? I'm in an R trivial monoid. I read A, B, and I'm in an R class. I read another A, I am in the same R class. My question is, if I read another A, will I stay in the same place or fall down? You understood the question?
You will stay.
No.
Okay. So I am getting recognized by an R trivial monoid. Okay. I'm in an R trivial monoid. I read a word AB. Okay. And I am in some particular R class. Let's imagine I am here. Okay, I'm here. I read another A and I continue in the same R class here. My question is, can I read another A? If I read another A, will I stay here or will I fall down?
You will stay there.
Stay there. Yeah.
You will have to stay there. No?
So why do you say you will stay there?
So essentially, we see that
Because
if
AB are equivalent to ABA, and if you fall on ABA, then you should have already uh, fell down on AB.
Yeah, exactly. So AB is R equivalent to AB A, and therefore A should be, so ABA is actually equal to AB. Therefore AA should be is equal to ABA. So I mean I'm writing letters, but what I here mean is the homomorphic image, yeah, H of AB. You understand what I'm saying?
Yes.
Yeah. So maybe. Okay. So now that we understand that, so how will can I write? How can I characterize this language? I am in one. So when I start my word, I am in one, and I see some letter. Let's imagine I see some letters A0. Okay. A0 is a set of letters. When I see A0, I'm still in one. I'm not moving from one. So I can still keep on reading how many ever times I want to see A0. And then a letter comes A1 and I fall down the R class. And I am in a new R class. And I can continue here for some when I see some letters A1 star. And then I see an A2 and I fall down. And then I can see some letters A2 star and so on till I'm in some final R class AK, and I see some letter AK and I fall to an R class, and then I continue there for some time. There's A0. Okay, so if we continue reason like this, we will hit on regular expression like this. That's what we are going to prove now. Okay, we are going to prove that the languages characterized by are trivial monoids are disjoint unions of the form A0 star A1, A1 star A2, A2 star A3 up to AK star, where A0 is a subset of A minus A1, A1 is a subset of A minus A2, and so on. All right.
So this appears very close to the ideal decomposition of downward closed languages. So is there any connection between this and that?
Actually, we will come to downward close language, not downward close, upward close languages, because our trivial, J trivial languages are piecewise systemic. But this kind of things are called polynomials. Okay, and it's not exactly polynomials, but you will. Uh, uh, but there is no direct connection, but there is similarity everywhere. Okay.
Okay.
Yeah, that's what I was saying in the beginning, that it's not very important, this doesn't have any connection with others, but you will see some ideas here which are common to a lot of things. Okay, so our point is to prove that this is the case. And okay, so first let's prove a characterization in terms of automata. The same idea, but we will state it in terms of automata. So you will see a deterministic DFA is extensive if there exists an order less than or equal to such that on stage Q. What is an order? Order is, what we mean by order is usually a linear order, okay, or a partial order. So we generally in automated theory, generally in mathematics, when you call what you call an order is just a partial order, whatever we call as a partial order. So, but in this case, you can complete the partial order to make it a linear order also. But we will just take it to be partial order. Order on states Q says that for every A in A, P is less than or equal to P dot A for each Q. Okay. So let me explain the terminology. You generally you say if you have a, let's imagine you have a function from real to real, and then you say f is extensive if x is less than or equal to f of x. Okay, this is different from saying something is f is monotone. When you say something is monotone, if x is less than or equal to y, then f of x is less than or equal to f of y. That's what you call monotone. So there is a similar distinction between an ordered automata and an extensive automata. Ordered automata is you have an order on the states, and whenever if p is less than or equal to q, then p dot a will be less than or equal to q dot a. That's what an ordered automaton is. Here it is called an extensive automaton because you are saying that every time I take a transition, I'm going to a bigger state. Yeah. Is it clear, this definition?
So here the function f will be the transformation function of the letter A.
Yeah, so here it will be just yeah, the transition relation. Yeah, I mean the transition relation will be like a extensive function, but it's a DFA. So the transition function, it's a function. Yeah, the transition function is extensive. Or in other words, for each letter, the transition function is extensive. If you label your states, you will be able to label your states by numbers in such a way that the transition function on each letter will be an extensive function. Yeah.
Yeah.
So if every DFA would be extensive, right? If you just set the order such that all states are equal.
Yeah, but we are talking about partial orders. So if you two distinctive state, if you have two distinct states, then they should be different. Partial orders are in particular anti-symmetric. So you cannot have p less than or equal to q and q less than or equal to p and
Oh, right. Yeah. Right.
Okay, so that is what is an extensive DFA. Let's prove that so first let's prove that position transition monoid of an extensive automaton is R-trivial. Okay, so once we show this, yeah, Transition monoid of an extensive automaton is R-trivial. Let's prove that. Nothing complicated. So let's imagine I have F and G. Elements of the transition monoid. Okay. Let's imagine F is R equivalent to G. So what does that mean? So you can imagine F to be transformation on some letter U. Let's call it WF and WG. Yeah, I have two words. WF is a word on which you get the transformation F. WG is a word on which you get the transformation G. Yeah. So now if they are equivalent, that means that if they are equivalent, it means that there exists some words U and V such that maybe I shouldn't maybe let me try it some other way. So let P be S, P be in Q. Then F is R equivalent to G means that can somebody help me here? Are you following what I'm doing?
Yeah, so now you want to consider another function h, which will be an
Yeah.
transition function. Then you want to show that fh, so makes us that f is equal to gh, and similarly for some h prime, g is equal to fh. But what it would actually mean is that if you go from, if you apply that function to any state p, then f will take you from p to some q, and then q to some r. And can you write this in this way?
Yeah. I'm still trying to figure out what is the best way to write this. So basically,
So F and G are just transition functions, right?
yeah. F and G are some transition functions.
Yeah, so then if if F and G are equivalent, that means, as Dhruv said, there would be like another functions, two functions, say I don't know, H and uh, K, such that F is equal to GH and G is equal to FK.
Yes.
Right?
Yeah. So I
And,
can write F is equal to GA, GY,
yeah,
X, and G is equal to FY.
and Fy, X and Y are also functions.
Some
And
X
which are extensive functions.
Yeah.
Yes.
T of transition monoid. Okay. Excellent. So now, if I take a word, so f is a function from Q to Q.
Yes, and for functions, multiplication is just composition, right?
Yeah.
Yeah. So
so if I have
so what exactly are we trying to prove? We are trying to
I
show
want
F
to prove
equal
that
to
f is
G.
equal to G. I want to prove that f is equal to G.
Right.
Okay, but
So
the
then,
point is that I don't know if I look at f of p, okay, if I have a state p, and if I look at f of p, which will be smaller than, no. So if I look at G of p, which will be smaller than G of,
X of G of X of P,
yeah, G of X of p,
because they are extensive,
yeah, which will
and
be
which will in turn be
equal to
yeah,
f of p.
yeah, and similarly the other direction.
Yeah, similarly, f of, yeah, this is what I wanted to avoid. Now it looks like f of p is smaller than or equal to fy of p, which will be equal to g of p. So therefore, f of p is equal to g of p for all p in Q.
Why did you want to avoid this?
Because it doesn't, I wanted to write it in terms of states, not in terms of functions, because now it looks like looks complicated. What I meant is,
So F of P and G of P all are actually just states, right? I mean, they're written as F of P, but they're actually, they belong to Q, right?
yeah.
So I mean,
So
But
what
if
you could do
everybody
is,
understood, then no problem.
yeah, I mean, instead of F and G, you could have taken any word which will create the transformation, and then apply that word transformation on the states. That's the same thing as applying the functions on the states,
Yeah.
right?
Yeah. Okay, so I hope everybody understood this. I mean, it's not complicated. It just means that you just have to visualize a little bit. So transition model of an extensive automaton is hard to get. Now let's try to prove the other direction. If L is recognized by an R-trivial monoid, then there is an extensive automaton for that. Automaton for L. So I have a monoid M recognizes L. Okay. I have a monad L recognizes L. I mean M recognizes L. So actually I can construct a automaton which recognizes L. What is that automaton? That automaton is
Just
one.
elements of the
Yeah,
states.
just elements of the singlet. M2, M3, etc. Okay. And on letter A, M1 will go to M dot H of A. Okay. And so on. So now this is an automaton. What is an order in which makes this an extensive automaton?
So we consider the J order of the elements, but we make all the elements inside a J class to be non-comparable, and then we revert all the orders because we are writing P less than equal to PA.
Yeah. So we don't have to go to the J order. We can actually take the opposite of less than or equal to R. Less than or equal to R is a partial order. Yeah, because it is since it is R trivial, we already know that less than or equal to R is a pre-order. Pre-order is an order which is reflexive, transitive, reflexive and transitive. So just to make it an order, we just have to make sure that it is antisymmetric. So, but we already know that it is R trivial, therefore it is antisymmetric. So less than or equal to R already satisfies the order is a partial order. But the problem is that I want M1 to be less than or equal to M dot H of A. But actually M dot H of A is smaller than or equal to M1 in the R ordering, less than or equal to R ordering. So we make the opposite of less than or equal to R. Sometimes you just call it greater than or equal to R. Okay. So greater than or equal to R is the opposite of less than or equal to R, makes M an extensive automaton. Okay. Is that clear?
Yeah.
All right. Okay. So now let's prove the characterization theorem. Um, characterization. Languages recognized by extensive automata are of the form disjoint union of A0 star A1, A1 star A2, AK, AK star, where A0 is a subset of A minus A1, AK minus 1 is a subset of A minus AK, maybe I may. Yeah, languages recognized by extensive automata are disjoint unions of languages of the form A0 star A1, A1 star A2, AK star AK, AK, AK star. Where, yeah. All right. So, okay. So let's prove. We have to prove both directions. Let's prove the easy direction. What is the easy direction here? Both directions are easy, but how do we go from the regular expression to the automata? So, for instance, yeah,
When the non-looping edges give the partial order.
pardon?
The non-looping edges give the partial order.
Yeah, so this will be 0, 1, 2, up to n or k, and then k plus 1. So if I put the states as 0, 1, 2, 3 up to k and k plus 1, then uh, we get an ordering of the states. Yeah. So this automata recognizes this language A0 star, A1, A1 star, A2 up to AK star, AK star. But now I see that we need to make an NFA of this kind. We will have different regular expression. So let's do the other direction, then we come back to this and discuss the NFA. How do we do the other direction? If I have an extensive automaton, how do I come up with a regular expression? How do I come up with an extensive? I mean, if I am given an extensive automaton Q, A dot I and F, how do I come up with an extensive regular expression for this?
So will A not be since it's a deterministic extensive automaton, I is a singleton. So we can say that the loop, so all the transitions from the singleton to itself, those will be A naught. Then all the transitions going from this initial state to other states, they will give rise to the first set of disjunctions, basically the first possibility of like the first separation. So it'll be like the union of say a1 plus a2 plus a3, like some ai's,
Mhm.
which we will distribute later. Then again we take the respective loops and we get a disjunction of since it's extensive, it's never possible to go from a word back to itself by reading some word. Go from state back to itself by reading some word.
Yeah,
Like after
but if I am given only the automata, I don't know anything else. How do I write a regular expression of the
So
previous kind?
yeah, that's what I was saying. So
Yeah.
so a naught star. So I'll just tell
So what will
like
be a naught? What will be a naught?
the loop transitions from a state to itself of the initial state.
Yeah. So basically, what you're saying is that any run can be split to some Q0, Q0, and then A1, Q1, Q1. So let's call this U0, U1, A2, etc. Yeah. So in any run, you will have at most k false. Yeah. Because your transitions are going from sorry, at most highs. It's not falling. It's you start in a state, you continue in that same state for some time, and then you climb up, and then you continue in the same state for some time, then you climb up, then you continue in the same state, and so on. And you can do it only as many as the number of states times. So clearly there are no loops. Yeah. So uh, you look at all uh, such transitions, all sequences Q0, A1, Q1, A2, Q2, AK, QK. Okay, that means that on Q0 you have a transition on A1 to Q1. On Q1 you have a transition on A2 to Q2, and so on. So you over all such sequences, you make a Q0 star A1, a Q1 star. So a Q0 is all the letters such that Q0 dot A is equal to Q0.
Yeah, and non-determinism, sorry, determinism makes sure that A1 is not in AQ0.
Yeah. AK, A, Q, K star. So union over all such sequences. All sequences. This is what your regular expression is. Yeah. So actually here one problem I see is that I have stated the definition extensive automata for a deterministic automata. But when I come here, if I have disjoint union, I will have to take disjoint number of such automata, and that will be non-deterministic. You understand my problem?
Yeah. No, so what we can do is since hold on. Now, is it possible to have another state which will act as the sole initial state? No, right? That might bring in non-determinism, is it?
Yeah. So I think you can make all the definitions to be non-deterministic. So what will change? So if you make all the definitions to be non-deterministic, transition monoid of an NFA it's complicated to build transition monoid of an NFA. So all these places it has to be deterministic, and this is also deterministic. So we have to adapt this regular expression so that it becomes so how do you make this construction so that it becomes deterministic? One possibility I see is it's not easy. You can make such automata for all the different things, each of the different regular expression, and then you can take the product automata, and the product automata you can make it to be you can follow the same partial order. You understand what I'm saying? Hello?
So take like asynchronous transitions kind of.
Yeah, so basically you have DFI for each of these regular expressions. Then you build an automata like this for each of them. You take their product. Each of them is partial order. So you make a for the product automata, you take the partial order which is the intersection of these two orders. That means the 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 tuple xy is smaller than or equal to x prime y prime if x is smaller than or equal to x prime and y is smaller than or equal to y prime. Okay. And you will be, since this automata is a complete automaton, you will actually see that the product automaton will also be complete. That means any two states will be comparable. Okay. And that automaton will accept exactly one of the input because each of these regular expressions are disjoint, so it will accept exactly one. All right. So this is what is R trivial languages. What about what about L trivial? Can you tell me what will be the regular expression for L trivial? And what will be the analog for automata for L trivial? That's an interesting question. Can you guess? What will be the automata for L trivial? For R trivial, we have extensive. For L trivial, what will you do?
Something like, so for R trivial, we have an automata where the states kind of go on increasing, right?
Yeah.
So maybe something like states, an automata where the states decrease.
Yeah, but that is not going to help you, because in R trivial, what we are saying is that you are attaching to the right. Yeah, the usual automata is actually respecting the R order. You are attaching things to the right. So if we are going to talk about the L trivial, you can no longer take the same automata model. Where you attach things to the right. You have to take.
So I was thinking
Yeah.
some sort of coextensive thing, which means like if you go back a step, which means like if you're going from P to A by like from P to Q by reading a letter A, then Q is less than equal to P. No, I mean,
Yeah, so
like,
that's what I'm saying. So if in the usual automata,
Okay.
you are actually starting with the empty word, then you're attaching A1, then you're attaching A2, then you're attaching A3, and so on. That is our automata. No matter whatever you do, it will be, you can, if you play around with the same, I mean, you start with the same definition, there is no way you can do an L trivial characterization.
So do we need codeterministic automata in this case?
Yeah, even codeterministic automata is not corresponding to L trivial. This one. What is codeterminism?
Oh.
Just for
So
those.
you just reverse the transition, it becomes deterministic.
So basically, determinism is on a letter, on every state, on every letter, you have exactly one transition to some. Yeah, codeterminism means that for every letter, you have exactly one transition coming into that state. That is what is codeterminism. Yeah, but even codeterminism does not help you for R trivial. But I will leave as an exercise. So what you will require is, you will require to make an automated model where you read the last letter A, then you attach the n minus 1 to it, then you attach n minus 2 all the way up to A1. Okay. So you will read the letter from right to I mean, instead of reading from left to right, you will start reading the letter from right to left, and then you will do the same extensive thing, and then you will write regular expression for that language. Okay, so it will start reading like, it will have exactly the same form, A0 star A1, A1 star A2, etc. up to AK star. But now you will say that AK is a subset of A minus AK, and so from this right you will say that I have some letters, and then this letter is not there in this, and then you have some letters, and this letter is not there in this, and so on. Okay, so do it as an exercise. All right.
Sir?
Yeah.
So if a language is recognized by an extensive automaton,
yeah,
is the reverse of that language also recognized by an extensive automaton?
Reverse of that language. Reverse of the language need not be, because if a language is L trivial, if the language is R trivial, then the reverse of that language will be L trivial.
Yes.
Okay. So then you won't be able to, it won't be recognized, it will be recognized in an extensive automata which reads the input from right to left.
Okay, yeah.
Okay. Yeah. So basically, when you get you have the expression for R trivial, and if you take the opposite or the reverse language, you will have an L trivial language. Okay. All right. So in the next class, we'll start dealing with J-trivial languages. So unlike R-trivial and L-trivial, J-trivial languages are one of the most well-studied language classes in automata theory. They are called piecewise testable languages. They were first characterized by Imre Simon in 75. So Simon is very famous. Simon is a superstar in automata theory. So many things are named after him. Simon factorization theorem, piecewise testability. He also proved locally testable characterization. A lot of things. Okay, and yeah. So by Friday, let me know what topics you choose, and then we can start the presentation in 2 weeks' time. Okay.
Yeah, sure.
All right. Okay, then we'll meet on Friday.
Okay. Thank you, sir.
Thank you, sir.
Thank you.